couple of parts. So we have our anode, we have our cathode part. Obviously, in the anode part is a solid electrode. For example, if this was zinc, we would also have some zinc guys floating around with their ion form connected through a wire. There's a little voltage action happening. And say on the other side, if that's copper, then obviously we would have some copper ions floating around. Anode is where, again, oxidation occurs. Reduction occurring over there at our cathode side. We also have, connecting the two here, a salt bridge. Again, that salt bridge, really important, as we talked about, to sort of keep the overall charges in each sort of component, basically without building up the wrong type of charge. So as we talked about last time, if you don't have that salt bridge, you will sort of build up a really big positive charge on the anode side, which would not be good for those electrons, which obviously are traveling in this direction. And then obviously you would build up a more negative charge on the cathode side, which again would not be good for the electrons. So by sort of the salt bridge having a electrolyte in it, it basically will send the proper ions onto either side. So negative guy will go this way, positive guy will go this way, and that will keep the overall sort of charges what they need to allow those electrons to go. We can calculate E of the cell by taking E of the cathode minus E of the anode. And remember that if we do sort of the subtract version here, we are not going to change the sign that we see in the SRP table. That is why it is subtract here. Basically, we'll change the sign for you because the anode should be a oxidation reaction, which means it should be reversed. And again, that negative there will change the sign for you. We also talked about that if in the lack of any information given to you in terms of how the reaction is taking place, it is the more positive SRP value that should be your cathode. And obviously the more negative value would be your anode in that particular case. You can as well add these together, but you would need to change the sign on the anode one yourself, and then you could add them together. We also tied this into our delta G minus NF of E. Once again here, F is Faraday's constant, which is our 96,500, and is the number of moles. And what we saw here was if we end up with a positive cell voltage, with the negative being here, that will end up us with a negative delta G, which means it should be heading towards products there, being kind of spontaneous. Vice versa, if obviously we head up with a negative cell voltage, that negative and this negative will then turn our delta G into a positive, which means, again, a non-spontaneous sort of process would occur. We also saw one that involved the equilibrium constant, and that is RTNF natural log of K, I believe. And this again is our cathode minus anode. R is the 8.314 version, T is the temperature in Kelvin, N is moles, and F is Faraday's constant. And that obviously is our equilibrium constant that we would want to use. And if we were sort of under non-standard conditions, we could have the Nernst equation here, which is natural log of Q in this case. And once again, this would be sort of our E under non-standard conditions, our E, which would be our cathode minus anode, Q being our reaction quotient of products divided by reactants, using obviously the coefficients like normal when we do that. Any questions on any of those stuff we talked about, I think, last time? Okay, so I think we had one more example here that we didn't get to. So why don't we do this one? For the following, why don't we just do the calculating of the E and the K in this case? See what you come up with. This again is our SRP sort of table information given to us. Okay, let's take a look. So we want E and also K. So obviously we can get E by taking our E of the cell will be our cathode minus our anode. So in this case, we want to kind of figure that out. Probably going for the chromium there is going to be the easiest way to maybe do that, is +2 and +3. So we can see that the chromium is becoming more positive and it is going through oxidation, which means by default, this guy is going through reduction, which he is at like a 2.5 to like a 2, I think, on that side in terms of oxidation states. And that means that this guy here would be our cathode, and that would be our anode in this case. And if we plug that in, taking our cathode, and here I am not going to flip the sign, so I'm just going to subtract the two values, and it will change the sign for me. And it looks like they're 68, maybe 67. 0.67 volts. Any questions on that there so far? Once we have that, we can obviously use the equation that had the equilibrium constant in it. Should look something like this, I think. We pretty much have everything we need on the left-hand side of the natural log. Our temperature, we do need to obviously convert there to a 298. The number of electrons, if we balance this out, probably looks like a 2 would probably work there, right? Got to multiply a 2 to everybody. So it looks like N would equal 2 in this case. At this point, that is everything we need. So we'll do a 0.67 is equal to 8.314. Our 298 divided by our 2 and our 96,500 and our natural log of K. At this point, I'm just going to kind of clean up everything right about here. So I'm going to go 8.314 times 298 divided by a 2 and then divided by a 96,500. That will give me a 0.67 is equal to 0.012837 natural log of K. I'm obviously going to bring that to the other side and divide it. Maybe hit the right number, 0.67 divided by that number. That's going to give me a 52.19 equals the natural log of K. And do a little E of both sides there. Going to finally give us a K here. Call it 4.6 to the 22, looks like. Questions on that one there? Now, once again, when we sort of look at these values here, they should sort of agree with each other. We do have obviously a positive voltage, which means we should have a negative delta G, which all that means we should be heading to the product side. And if we're heading to the product side, that means we probably have more products than reactants. That means that my K value should be a large value. And obviously that would qualify as a large value in that case. So again, those guys should agree with each other. Any questions on any part of that calculation there? Question on galvanic cells, the calculations that we did before. Okay, the next thing we're going to kind of talk about is a little bit about batteries and, you know, some different types of batteries. And just really what you need to know is just some of the similarities of batteries, obviously, to a traditional galvanic cell, and obviously some of the differences. You're not responsible for any specific battery or battery equations or anything that we see. So a battery really is just a galvanic cell or sometimes a series of them placed together that can be used obviously for direct electrical current. The nice thing about it, obviously different than a traditional galvanic cell you could build in the laboratory, is they are self-contained. You don't have to put beakers of solution into your calculator or anything like that to get it to work. So it's all sort of self-contained. Also, sort of in place of a salt bridge, they oftentimes will use some type of electrolyte solution, like battery acid that we sometimes refer to, that we see oozing out, in place of sort of a salt bridge to kind of keep everything flowing in terms of the electrons. And if we look at a battery, for example, this is what's referred to as a dry cell. I'm going to go with the Duracell on this one here, the copper top. And this is basically a cell without sort of a fluid compartment. We have an anode, which is the zinc can here, and it's in contact with a layer of MnO2 and an electrolyte. We also obviously have a carbon rod that's through here that is working as our cathode. So again, you pop that in there. There's wires right in your device, and electrons kind of go out through the wires and do their deal, and obviously end up back over there at that side to sort of complete the whole circuit. We also have in here some zinc chloride and ammonium chloride. Again, is a sort of electrolyte sort of paste in there, sort of acting like a salt bridge to kind of keep everything really flowing. No matter what size you got going on this particular type of battery, they will all give you basically a voltage of 1.5 if they're fresh. We do have different sizes, obviously, like AAAs and AA's and CDs and all those kind of things. They just can obviously do the reaction a little bit longer, right? Because their capacity a little bit bigger. But what we do see here is our zinc here going from 0 to +2, so going through oxidation, and then really our Mn on the bottom part there going through reduction that's happening. Again, you're not responsible for obviously any of these reactions or anything like that that is occurring. Another type of battery is a mercury battery, and that's kind of similar in a sense of obviously a lot of batteries are obviously similar. It's used a lot in medicine and electronic devices. It's a little bit more expensive than a dry cell. Here we do again have the zinc as our anode, and our cathode, sort of the stainless steel there. It has a really strongly alkaline electrolyte. Alkaline means basic, right? Hence why there is some potassium hydroxide sort of happening in there, which is a strong base. Again, that's going to keep everything flowing, kind of like the salt bridge. There's no change in electrolyte composition during operation. Gives you a little less voltage off of these guys, 1.35, but it has a much higher capacity and a longer life. And if you ever look at sort of batteries and their overall reactions, if you end up with a lot of solid that's there at the end and the beginning, it's actually really good for sort of longevity for a battery, and also for recharging batteries as well. That's also really good to sort of end up like that. Here we got our, once again, our zinc going from 0 to +2, our mercury here going from +2 to 0 in this case, again being reduced in that reaction. Lead storage battery, which is like our car batteries, a traditional sort of car battery is basically 6 cells sort of joined together. Each of them kind of puts out like 2 volts, which gives you your 12-volt battery that you have. Both usually the anode and cathode is immersed in sort of a very strong electrolyte like sulfuric acid. It's enough obviously to start your car when you need to and get all the electrical systems and all that going, except when you're really late, right? And then it's not enough to start it. Your battery dies and they go, is it the alternator or that kind of stuff? So we do have alternators and those type of stuff, right? So we don't drain sort of the battery. It's rechargeable, which means, you know, through the process of driving, right, it sort of recharges it as you go through it. Sometimes you live in a really cold environment. It's a little harder to start your car because all the inner parts gets a little bit more viscous and not really moving around very well. Here's sort of a cross section of a car battery. Don't cross section your own battery. But again, you can see basically the series of cells together here, given our voltage and our cathode and our anode there. And nowadays, batteries oftentimes are not even like in the engine part, right? They're like sometimes on the trunk or underneath the seat, but they do run like these guys in the engine part. So in case you need to jump your car, you can still do that usually. Here we do see the lead going from 0 to +2, again being oxidized in this particular case. And on the bottom here, we have our lead going from +4 to +2 being reduced in this particular case. Again, you do see a lot of solid there in the overall reaction, which again is really good for sort of long life and sort of rechargeability of batteries. This is a lithium solid state battery, and it is an anode that has sort of a graphite material that allows really when this guy sort of goes through oxidation, those guys to kind of go on through to the other side. The cathode is some type of transition metal that can hold those lithium ions to go through there. It can be recharged hundreds of times, and lithium is actually a light metal, right? It's kind of number 3 there on the periodic table, very light molar mass, which is also why they've used lithium type batteries for drills and all those other type of things, because it's lightweight as well. This is a fuel cell. Fuel cell is not necessarily a traditional battery, but sort of operates similar. We got a flow of oxygen and hydrogen into here, along with a very hot potassium hydroxide sort of solution. Anode here, giving our electrons over to our cathode. This is what they kind of wanted cars to usually run on or try to do, but now we're more of a hybrid battery type of situation. But this idea here was that it would only obviously produce water, which would be really good. And again, our hydrogen going from 0 to +1 being oxidized, oxygen going from 0 to -2 being reduced in that case. And again, the nice byproduct there is water. Obviously, we need a constant supply of these guys to obviously allow this to run. This would come from the air, usually in a car situation. Thus, we would need a lot of hydrogen stations to fill up at. And obviously, we don't have a lot of those and stuff like that. So never really took off. So for batteries, again, you just need to kind of know a little bit about them, similarities and differences, again, to a traditional galvanic cell that you would build in a laboratory. Let's talk a little bit about corrosion. Corrosion is returning really metals to their natural state. It is really when metals kind of go through oxidation that occurs. So at 1/5 of the steel was there to replace the rusted out metal. Any metal that has an SRP value, basically less positive in oxygen, is susceptible to going through basically corrosion and oxidation. And that is because if you have oxygen and you have a metal, and the metal has a less positive SRP value, that means that this guy would be more positive and he would act as the cathode in that reaction. The metal would act as the anode, and that means all the oxidation is going to occur on the metal there. And basically that is what corrosion sort of is. So you get a nice spontaneous corrosion process happening. Now, not all necessarily corrosion or oxidation of metals isn't necessarily a truly bad thing. Some metals can form a layer up on top, which actually can protect further metal underneath, as it kind of makes this protective layer, preventing further sort of oxidation occurring to the metal that's underneath. So for example, aluminum's example that it will sort of make a nice layer of some aluminum hydroxide there, or oxide, and basically will sort of protect the metal that's underneath there. But something like rust, obviously not so good, because when you form rust, it sort of falls off, if you will. And what that obviously does is then expose new metal to further oxidation that will continue to sort of fall off and continue to do that until you see the metal has probably been like almost rusted through, right? You could almost go right through the thing because there's no real metal left at that point. Copper forms a nice greenish patina as it goes through oxidation. Silver tarnish is silver sulfide. And gold with a SRP value of 1.5 is larger than oxygen, so gold will not really go through any type of corrosion. And that's because when something like gold and oxygen gets together, because gold is more positive, gold acts as the cathode, oxygen acts as the anode, and that means no oxidation happening of our gold in this particular case. Now, we talked a little bit there about rust, and really 3 components that you really need for rust to form is a little bit of iron, a little bit of oxygen, and a little bit of moisture is pretty much all you need for rust to form. And there's a lot of non-uniform sort of parts on steel where, kind of moisture could settle. And that's sort of a breeding ground for everybody to come together to sort of start the formation of rust. Iron that gets oxidized actually to iron 2, and then further sort of oxidized to iron 3 in this process. And here's a much prettier picture of that. Again, these sort of points where the moisture can sit along with the oxygen, which is obviously supplying some O2 or from the air, and our oxidation occurs. And again, this falls off, more of it gets rusted away, costs a lot of money, sad sort of thing that happens there. Now, there are ways that we can prevent or sort of slow down or prevent some corrosion. So let's talk about some ways that we could do that. Obviously, you could add some type of coating that would protect the metal, right? So some type of paint or metal plating, right? They sell the classic Rust-Oleum paint, right? So it should hopefully prevent rusting of your metal. You could also, like I said, use something like chromium and tin to plate it. They will oxidize and form, again, a more protective layer over the metal that you're trying to protect. Zinc and galvanizing is another way. Zinc is a more active metal than iron. And if we look at the SRP values between these two, iron and zinc, it is actually iron that would be more positive in this case, which means that the iron would then act as the cathode. The zinc in this case would act as the anode. So all the bad oxidation will occur on the zinc, again, protecting the iron there in that case. And that's why it says zinc there is acting as sort of a sacrificial sort of coating for the steel. You could also alloy some metals together, something like chromium, nickel, and stainless steel. Sort of makes it almost like a noble metal, which makes it very unreactive and will not go through much corrosion. Cathodic protection is another way that's commonly used, especially when they would bury like iron tanks underground, which obviously has a lot of moisture and stuff like that. So they could attach something like magnesium to it, as we'll see in the next picture. And by attaching magnesium, magnesium is actually a much better reducing agent than iron. And because it's a better reducing agent, that means it will go through oxidation. So again, once again, all the sort of oxidation and corrosion part of it sort of happens at the magnesium spot away from the iron there. That's a part of your tank that you buried. So it doesn't sort of destroy the tank that you decided to bury, kind of like this. So again, all oxidation happening over here. This guy would act more like a reduction, and again, preventing significant sort of breaking down of this sort of storage tank. Again, obviously at some point, this guy's gonna get used up, so you gotta kind of replace it and keep it going. Any question on corrosion? So for corrosion, you know what it is. A couple ways to protect against corrosion is good. Any questions on any of that there? All right, last thing we're talking about in this chapter is electrolysis. Electrolysis is a process in which we basically apply electrical energy to make a non-spontaneous process basically occur. So for example, if we have sodium chloride, again, you can pretty much heat the heck out of it and you will not get back its elemental form, if you will. You will not get back the sodium metal or the chlorine gas in a normal situation, but you can apply a sort of external battery and basically break apart these guys into chlorine and sodium coming out. So in this case, our anode is actually our chloride, because our chloride we're going to take back to chlorine gas, which means it is going from -1 to 0. That means if you follow our little number line thing, it is going in that direction and it's going through oxidation. So it is actually going to be our anode in this case, while we would be taking the sodium ion back to solid sodium, which would be going from +1 to 0, with, once again, if you follow that, would be going in this direction, going through reduction. So it is sort of the opposite, right? When we kind of put it together, it is the sodium that loses electrons, right, and gets oxidized. But in this case, we're kind of putting it back together the other way. So it is the sodium here that is getting reduced. So that is why it's on the cathode side. And that's what we see here. That way we end up back with our sort of elemental forms, if you will, of that ionic compound. Any questions on that there? Same thing could happen with water. You could take some water, add a little bit of acid to kind of help it along, and basically get a 9-volt battery with the proper electrodes, and you basically can do this. And it will basically break apart water, obviously, back into sort of its components of hydrogen and oxygen gas in this particular case. And that's what we see here in this picture and in a real life picture over here. We see the bubbling occurring, which is our hydrogen gas and our oxygen gas. And once again, in this case, it is the oxygen that is going through oxidation, as it is really going from -2 to 0, right? And again, going from -2 to 0 means it is going through oxidation. The water is really the hydrogen going from +1, if you will, to 0 in this case, going through reduction. So again, the opposite of sort of putting it together, breaking it back apart. It usually, like I said, does require some acid. So you got to add a little bit of acid there. So sometimes in electrolysis problems, they will not scream in bright lights that you are talking about the electrolysis of water. They will just say something about using sulfuric acid or dilute sulfuric acid or some type of acid. That usually indicates that we're talking about sort of the electrolysis of water that occurs. Obviously, our gas is in this empty spot. And why do we have more hydrogen than oxygen? Because it's H2O, right? So twice as much hydrogen, and we get oxygen, right, in that little space there. So let's talk about sort of electrolysis problems. They sort of run in one of two ways. They oftentimes will give you the current or the amperage at which you are running a electrolysis cell for, and kind of how long you're going to be running it from or running it for. And that's where this relationship could come into place. A charge or a coulomb is equal to the current in amperage times time, which means a coulomb is equal to an amp times seconds, if you will, which means an amperage there is a coulomb over a second. So that is a way you could kind of convert the amperage they give you into coulombs per second. Obviously, the time in this case would need to be converted to seconds in most cases so that the units here cancel out correctly. So if they say they run it for like 3 hours, you probably need to convert that guy into seconds so everything cancels out. Once you do that, you typically will take your coulomb per second, you will times it by your seconds and time that you ran the cell for. That will give you basically a coulomb of charge. At that point, you can use Faraday's constant to do a conversion between coulombs and moles of electrons. And at this point, you will then have moles of electrons. This is where basically the two half reactions would come into play for the anode and the cathode side of your electrolysis cell. And in that, you would have at some point, you know, some electrons and maybe, you know, some type of metal here. You would do a mole to mole relationship between these guys from the half reaction, and that will take you from moles of electrons to moles of whatever you're interested in. At that point, you have really kind of two options usually in these type of problems. The first option is they want to know, for example, how many grams you may collect. So once you get the moles of the element you're looking at, you obviously could use the molar mass to convert it into how many grams that would be. Also, sometimes they're interested in how much volume of a gas you collect, like the hydrogen and the oxygen example. And since those are gases, we sometimes will need to use our good friend PV equals nRT, or the ideal gas law. where pressure, right, needs to be in units of atmospheres, volume needs to be in units of liters, temperature in Kelvin, obviously N should be moles, and the R here is actually our 0.08206 number there, liters times atmosphere, Kelvin, and mole. So sometimes in these electrolysis problems, you're collecting a gas, maybe chlorine gas, hydrogen gas, oxygen gas. So sometimes they're interested in how much volume you would collect. So sometimes you'll need to take the moles that you get at the end there and use the other information like the temperature and the pressure and stick it into the ideal gas law and solve for volume to figure out the volume of the gas that you would be collecting. Any questions on any of that there? All right, so let's take a look at one here. Actually, we'll skip that one. Let's take a look at this one first here. So how much calcium will be produced in an electrolysis cell of molten calcium chloride if a current of 0.452 amps is passed through a cell for 1.5 hours. So in this case, we're starting with calcium chloride, which basically means we have a calcium ion and a couple of chloride ions, right, that are happening here. And in this particular case, we're interested in the calcium. We're going to take the calcium back to solid calcium, which means my calcium here is going to be my anode or my cathode in this reaction. So it's going to go from +2 to 0. That is the cathode, right? That's going reduced. Yeah, that's being reduced. And really in this cell, it is the chlorides going to chlorine, right? Going from -1 to 0, which means it is being oxidized in this case. So remember, it's a little bit opposite of, how you put it together. We're sort of breaking it back apart. So the anode in this case should be our chloride, and the cathode here should be our calcium. Again, we're taking it from the ion form back to kind of their basic elemental form, sort of in each of these cases. Any questions on that there? All right, so now we could figure out, we're really interested in the calcium here. So we could start with the 0.452 amperage there. That is the same as 0.452 coulombs per second. I am going to run the cell for 1.5 hours. In 1 hour, there are like 3,600 seconds, I think. Yeah. So we could convert that into seconds at this point. So we take 1.5 times 3,600, gives us about 5,400 seconds at this point. So now that I have this, and the reason I needed to do this was so that the unit-wise, these two guys would cancel. So we want to make sure everybody's in the correct units. I can now really take the time I'm going to run the cell times the current at which I was running the cell for. So we'll take our 5,400 seconds, which is how long we're running the cell. We're going to take basically the amperage of the cell. The seconds will cancel. That will get us 0.452, 2440.8, I think. And these would be coulombs. At this point, we would use Faraday's constant to go from coulombs to moles of electrons. So this is pretty standard first step on these type of problems, is these few steps right here. We're going to do our 96,500 coulombs per 1 mole of electron. So we're going to divide up by 96,500. Going to give us, we'll call it 0.025 moles of electrons. Any questions so far? So really, like I said, these kind of first steps here are fairly common in these type of problems as to what you kind of need to do. At this point, we really could go to either one of the things. If it, if we were interested in both, we could do both. But in this case, we'll do what the problem asks, which is we're interested in the calcium. So once we get to moles of electrons, We could use the balanced half reaction to go from moles of electrons to moles of calcium. And what we see from the half reaction is every 2 moles of electrons give us 1 mole of calcium. So we're going to use that really as a conversion factor. So that's going to give us 0.025 moles of electron. 2 moles of electron on the bottom, so they cancel. 1 mole of calcium up on top there, and that would get us that guy divided by 2. 0.013 moles of calcium. And if I want to know how many grams that would be, I'm going to use the molar mass of calcium, which is 4008, I think, give or take. That look right to somebody near a periodic table? 4008 grams per mole of calcium. So if I times that by 4008, gives me about 0.51 grams of calcium. About 0.5 gram of calcium would be produced in the cell if you let it run at that amperage for about 1.5 hours. Question on any of those steps there. If I was interested in chlorine, I would do the same basic start, except at this point, I would then go to the chlorine half reaction and do the moles of electrons to chlorine. And since chlorine's a gas, perhaps they would give me a temperature and some pressure, and I could go into the ideal gas law and figure out the volume, or I could also just figure out the grams of the chlorine that would be produced as well. Question on any of those there? All right, so why don't you try one, which is the one we skipped. We'll go back to it, which is the water example. So if we run a cell at 1.26 amps and we run it for 7.44 hours, how much volume of each gas will produce at STP? So we're going to run basically this cell for, what did it say there? Well, 7.44 hours and 1.26 amperage, I believe. And we want to know the volume of oxygen gas and hydrogen gas at STP. STP is standard temperature and pressure. That's a pressure of what? 1 atmosphere and a temperature of 273, yeah. STP, yeah. I'll give you the reactions for you. And like I mentioned before, as you can see there in this question, you know, it really doesn't necessarily mention water, but it just says sulfuric acid and stuff like that. So again, that is sort of how you know it's sort of talking about water. Look here and see what we got going on. So really, once again, we're given the amperage of the current for the cell. We have how far we're going to run it for, or how long we're going to run it for. So really, again, the start here is very similar to what we did before. We need to get our hours into seconds. So we're going to multiply by 3,600 seconds. Will get us there. So we're going to take 7.44 times the 3,600, going to give us, looks like 26,784 seconds. Once again, our 1.26 amperage is the same as 1.26 coulombs per second, hence why we need to get this guy into seconds. So we're going to multiply those guys together. That's going to cancel out the seconds at that point, and we will end up with, looks like, calculator's hard to read, but I think it says 33,747.84 coulombs. At this point, this is where we're going to use Faraday's constant to really get us into moles of electrons, so we could then use our half reactions for each of it here. So we're going to take that number there, our 33,747.84, and there's a dot right there. Coulomb, we're going to divide by Faraday's constant, 96,500 per mole of electron. And if we do that there, looks like 0.350, we'll call it, moles of electron. Any questions so far on the first part here? Now, once we really get to moles of electrons, that's where we can use, obviously, the balanced half reactions to get us to each of the elements that we're interested in. In this case, we're actually interested in both of them, the hydrogen and the oxygen. So we'll carry that number over to the next page here where we have our half reactions to look at. And we can see that we have 0.350 moles of electrons. From the half reaction for oxygen, it is 1 mole of oxygen gives us 4 moles of electrons. So we can do that real quick here. 4 moles of electrons gives us 1 mole of O2. So if we take that guy, do a little dividing by 4, gets us 0.0874 moles of oxygen. We would obviously want to do the exact same thing here for our hydrogen. Looking at our hydrogen, that is, if we multiply the 4 in, that is 4 moles of oxygen, 4 moles of electrons to 2 moles of hydrogen. So 4 moles of electrons to 2 moles of hydrogen, or you could do 1/2 as well. Obviously, that's the same thing. And if you do that, gives us 0.175 moles of hydrogen. Any question on either of those there? And again, you can reduce that down to a 1-to-2 relationship if you like as well. At this point, we should probably go into our ideal gas law since we are looking for a volume. And now that we have moles for each of those, and obviously we always have R, so we could do PV equals nRT. We'll do it for the oxygen here. And if we solve for the volume, it would be nRT divided by P. That would be our 0.0874, our 0.08206 liters atmosphere Kelvin mole, and our temperature of 273. I'll go high so I don't get in that way of that thing. I'll just move it. 273 Kelvin, all divided by our pressure, which would be 1 atmosphere in this case. And I'm just gonna up there a little bit. (273 Kelvin). All right, everything's going to cancel out here, obviously, except for liters, and that will get us the volume of oxygen gas at STP being like 1.96 liters, give or take, of oxygen. We could also obviously do the same thing here for hydrogen. Everything will be the same except that we will have a different moles, which would be 0.175, 0.08206, our 273 Kelvin, all once again divided by 1 atmosphere. And for our hydrogen, then looks like 0.175 times 0.08206 times 273 gets us about a 3.92 liters of hydrogen would be collected in this case. And that is a 2-to-4 ratio there of gases, right? Twice as much hydrogen as our oxygen. First off, any questions on those calculations? Could I have solved it a different way? I could have, if you remember this relationship, that since we were at STP, 1 mole of any gas equals 22.414 liters. So you could have just took the moles of either one, really, 0.175 moles, and times it by 22.414 liters. And should pretty much give you that number as well. So you could use that relationship, that is because it's at STP. That's the only time you can use that relationship, by the way, right, is at STP. Otherwise, you could clearly just stick it into the ideal gas law and not a problem. Question on electrolysis problems. Variation of this problem would be like they tell you how much you collected. Yes, you go backwards, maybe figure out how long you ran the cell for, or how much amperage you did, which is basically just the opposite direction, heading backwards. Any questions on any of that there? All right, that wraps up this chapter here. We will get a little bit into the next one. So just give me a second here to punch it up. All right, so the next chapter we're going to talk about is nuclear chemistry. I think it's 21. It might be 20. I think it's 21. It's 20-ish, I know for sure. So in this chapter, obviously, we're going to talk about nuclear chemistry and balancing nuclear reactions and some kinetics that involves nuclear chemistry. So let's talk a little bit about radioactivity. Radioactive nuclei spontaneously decompose into smaller nuclei. That is basically radioactive decay. If something does go through that, obviously it is unstable. Typically, wherever it starts from, if it does decay, the original guy is sometimes referred to as the parent. And the one that is formed as sort of a result of that decay process is what is referred to as the daughter nuclide. Nuclei is like the nucleus we sort of talk about. Any nuclei that have 84 or more protons are radioactive, which is for the most part your bottom part there on the periodic table. The real bottom row there is all those guys are kind of radioactive. There are different types of radioactive particles that we do come across, and some symbols that we do see in nuclear chemistry. Our good friend Rutherford, do you remember him? He did some experiments with some gold foil, right, and all that good stuff. Discovered sort of three types of rays. There are alpha rays. Alpha rays or alpha particles have basically a kind of +2 charge there and basically a mass number of 4. It is really the helium nucleus. So alpha particles in nuclear chemistry is sometimes abbreviated with the alpha symbol, or sometimes just helium is used to represent an alpha particle. So those are two common ones that are used there. A beta is kind of like an electron, and it also has a couple of symbols that are commonly used, like the beta there are really the electron. The gamma ray is just pure energy, so sometimes just like that. You might remember gamma rays from when you looked at electromagnetic spectrum, and it was pretty much past X-rays, has very short wavelength, right? So short wavelength means very high energy. It means you should not be just standing there and letting it hit you all day. Yes, it's just really, really pure energy. In addition, there are some other symbols that we'll come across very commonly in here. Sometimes unstable nuclei will emit what is known as a positron. It's like an electron with a better attitude. Thank you. I'm here twice weekly. So it is actually the symbol for a positron is pretty much the same symbols here, except that it is +1 that they use there. So they will use similar symbols for those guys, sort of a positively charged electron. Occasionally, there will be reactions where an electron capture will occur. Electron capture is pretty much what it sounds like. An electron on the reactant side basically gets bombarded into something. It hits something and it reacts with it. So that brings us to our good symbols that we oftentimes see a lot of in nuclear chemistry. Top number is our mass number, right? Mass number is the number of protons and neutrons in an element. Bottom number there left is our atomic number, which is the number of protons in the nucleus. Can you find both numbers on the periodic table? No. You can only find the atomic number on the periodic table. That is the number above the symbol. The number on the bottom is the atomic mass, not the mass number. If you want to calculate the mass number, atomic number, number of protons, electrons, or neutrons, they are all positive whole numbers. So good way to remember it is they have to be whole numbers. If you look on the periodic table, clearly most of the atomic masses are not whole numbers. Oftentimes people get confused by that because the mass number and the atomic mass are similar type of number in terms sometimes, but they are not found in the periodic table. Only the atomic number is. And here are some other sort of symbols that we very much come across here in nuclear chemistry. Some of these we just went over, but let's take a look. A proton is sometimes used, and it is also sometimes used two different ways to represent a proton. P for proton with a mass number of 1 and an atomic number 1, and hydrogen, which is also sometimes referred to as a proton, 1 proton and 1 as well. A neutron is also another very common particle. We see a lot in nuclear chemistry, and that is the symbol for it, mass number 1, atomic number 0. By the way, to find the number of neutrons, you do what with those two numbers? You subtract the mass number from the atomic number, right? If you take the mass number minus the atomic number, that does give you the number of neutrons. Here is our electron, our beta particle. And again, you can see it is basically kind of the same symbol as we see for our positron, which is a positive electron. And here's our two common symbols used for our alpha particles. Again, is wrong with the mass number and the atomic number that is there. So these sort of symbols you should be familiar with, and obviously the charges that go with them, because it's going to be really important in terms of balancing the nuclear equations to sort of figure out those numbers and know what those are. Any questions on that there? Yes, sir. How do you determine? We'll talk a little bit about it when we balance equations, but for our purposes, that's how you would figure it out based on sort of the balance equation and you know what you need to do that. Now, different sort of particles do penetrate, for example, lead further than others. So alpha particles only go 0.01. Beta particles penetrate a little bit further, and gamma particles keep going and stuff like that. So, you know, if you ever find yourself working with radioactive material, you should always figure out what type of emitter it is and make sure that you use the proper sort of protection. Sometimes you just need gloves and a coat. Sometimes you need a lot of lead and like concrete behind you, between you and the radioactive device. So it's always good to figure out what type of emitter it is and make sure that you are using the proper sort of protection. Sometimes, you know, people forget to mention these good things to you as you're working in places. Again, here's just some of those symbols that we see. Now, if you see just a beta written like that and nothing else written, it's probably pretty safe to assume that it is the beta particle. If it is like the positron or something like that, they typically will put something with a positive on there. So, you know, they'll sometimes put like just the plus up there and they'll tell you, hey, it's the positron one. So again, if you just kind of see the beta particle with nothing, it's probably safe to assume it is the beta particle and sort of the negative version of it. All right. So I think we will lay it up there. We'll say balancing nuclear equations for next time.